A common approach to examining the association between variables is a linear regression. Unfortunately, not every variable satisfies the assumptions for regression, such as being normally distributed. In the case of non-normal data, we can express our data as a function of some unobserved latent random variable that is normally distributed. To understand why this works, consider an ordinal variable movie rating that takes on discrete values from 1 to 5. Since it's natural to think the actual quality of the movie lies within a continuum, we can pretend that some unobserved variable exists that is numeric and also normally distributed. The modeling technique of regressing the discrete movie ratings on a set of predictors through a latent variable is known as ordered probit regression. The actual model can be represented as a latent variable z being regressed on x with the coefficients stored in beta. Then, to relate the latent variable back to the ordinal variable y, we pass it to a non-decreasing function g that checks which interval the z value is in and returns the corresponding discrete y value. So for our movie example, let's pretend we've already found beta and g. Now when we observe a movie that paid $5 to its director, had a hype score of 3, and did star Tom Cruise, then we predict our mystery numeric variable will be 35. Now consider 35 as an input to the function g. Looking at the thresholds, we see 35 is greater than 30 but less than 40. So our final movie rating is predicted to be 4. Pretty useful. But we wouldn't get beta and g for an actual problem, so how do we find them? Well, if we use normal prior distributions for the unknown parameters beta and the thresholds in g, then the joint posterior distribution of beta, the thresholds, and z, given y, can be approximated using a Gibbs sampler, which is a concept we saw in lecture. To see this, let's examine the full conditional distribution of our variables. First, the full conditional distribution of beta depends only on z, since y and g are only related to the betas through z. Next, consider that a multivariate normal prior for beta gives a multivariate normal posterior distribution. So now we know the expectation and variance for beta's full conditional distribution. We can use this information to update beta for each iteration of the Gibbs sampler, since it defines its distribution completely. Next, consider the full conditional distribution of z. When we're given beta, each zi is distributed as a standard normal centered around the prediction equation's expectation for that observation. However, when we're given g, then observing y for the current observation tells us that that z has to be between the thresholds corresponding to that y. This is a constrained normal distribution. To sample a value, we first sample from a uniform distribution with the endpoints corresponding to the probability to the left of our g interval values in the original distribution. So the g interval in the original normal distribution corresponds to a range of allowed probabilities in the standard normal distribution. From here, we convert this sampled probability into a value in the standard normal distribution with the inverse CDF. Finally, since the original normal distribution could have a different mean and variance from the standard normal distribution, we can scale the standardized value back to the original normal distribution. Now we're left with a sample from our original normal distribution that lies within the allowed interval. And lastly, for g, we know the value will be constrained based on the values of z and y, but not beta. Gk must be greater than any zi, where yi equals k, and gk must be less than any zi where yi equals k plus 1. This means we need to find the maximum and minimum values for these zi's to create the interval that gk must lie within. So if the prior distribution of g is normal, then the full conditional distribution of g is once again a constrained normal distribution where any gk must be greater than the set ak and less than the set bk, which are defined as the sets containing the maximum possible values a z could take on with y equal to k, and the minimum possible values a z could take on with y equal to k plus 1. Recapping, we have defined the full conditional distributions of beta, z, and g. Now it's time for Gibbs sampling to work its magic. After initializing beta, z, and g, we can begin iteration 1 of the algorithm. For each observation, we first sample a value for z based on the current values of beta and g. Remember that this involves sampling a uniform random variable in the constrained probability range, and then transforming the uniform random variable back to a valid zi value. After we've fully updated z, we can sample beta conditioned on z and g. This is just sampling from beta's normal posterior distribution. When beta is updated, we move on to updating g in the same way, but just sampling from its full conditional distribution. Once this is done, we've completed the first iteration of our Gibbs sampler. From here, we just continue to generate new samples for beta and G. Also, since each sample depends on the previous one in our Markov chain, it's helpful to only save every 25th value to reduce autocorrelation between samples. When you've run enough iterations, you'll be left with a list of samples for beta and G. To get the final estimates for these parameters, we just take the mean of all these samples. Going back to our previous example, we now have a way to go from our known movie ratings and their prediction data to a model that can be used to estimate the rating of a new movie with known predictors. Improvements can be made on our Gibbs sampler though. For example, if the ordinal variable has k categories, then G requires k-1 parameters, which is burdensome when k is large. But since we know G is non-decreasing, then if we observe data such that y1 is greater than y2, we know yi is the output of G for input z. Therefore, G of z1 must be greater than G of z2, and finally we conclude that z1 must be greater than z2. Following this chain of logic, we see that observing y tells us that zi is in the following set. This distribution does not depend on G, so the probability that z is in the set also doesn't depend on G. Therefore, our posterior distribution for beta can be given as follows, where the term representing the probability of z being in the set R given beta is known as the rank likelihood, and is what provides the information about beta without having to specify G. Now when we go to approximate the joint posterior distribution of beta and z, we no longer need G. The full continual distribution of beta doesn't change from before, since knowing z is in the set R doesn't give more information than actually knowing z. The full continual distribution of z is still a constrained normal distribution, but this time the constraint is that z is in the set R. Specifically, zi has to lie in the interval relating z to y using the logic from before. If we call these bounds a and b, then the full continual distribution is the same as the previous section, except that the constraints are determined by the z instead of the g. The Gibbs sampler basically works the same as before also, except that there's no longer an update step for G. So after the new algorithm runs, we'll have a sample of beta values to get our estimate for beta from. It should be noted that one drawback of using this rank likelihood approach is that it doesn't provide us with an inference about G, which describes the relationship between the latent and observed variables. If we need this information, then we're better off using probit regression. Finally, it's worth noting that because we assume the latent variables are independent and identically distributed normal random variables with a correlation matrix psi, we can actually examine the dependencies among our variables. To estimate psi, we first need to consider that every observed variable yij is generated by transforming its corresponding latent variable zij through a non-decreasing function gj. This is significant because it means that each marginal distribution of y depends on its own transformation function gj, not the correlation matrix. This is a Coppola model where psi captures the dependencies among variables while the g function controls the marginal distributions of each variable. If we once again use rank likelihood, we can attempt to estimate psi using just information about the latent variables. Start by defining another constraint set, R, so the rank likelihood doesn't depend on G. Next, we assume the latent variables are IID from a multivariate normal population with covariance matrix sigma. We choose the inverse Wishart distribution to be sigma's prior because the full conditional distribution of sigma will also be inverse Wishart. Now that we have a full conditional distribution for sigma, we only need a full conditional distribution for z. Fortunately, we previously stated that z is a random multivariate normal vector with a zero mean vector and covariance sigma, so the conditional distribution of a single zj given the other elements is a univariate normal distribution with the expectation and variance as follows. All that's left to do for this distribution is to condition on the likelihood information that z is in the set R, and now we have a full conditional distribution for both z and sigma. Gibbs sampling is the same process as before, just updating sigma and then z for each iteration until we're eventually left with enough samples for sigma to make an estimate. We can then transform our estimated sigma into the desired correlation matrix so that we can now see more clearly how each of our variables relates to one another. So these were 3 different instances of Gibbs sampling, letting us generate estimates for our parameters, starting with just conditional distributions. If you're interested in a real data example for these methods, I've linked my write-up in the description, which works through each using the current population survey from last September. Thanks for watching. Bye.